Hello and welcome to Calculus. This is our first section of the book, and really what I want to talk about is where this is going to go. So this section, don't get overwhelmed by some of the topics here. This first section is called the tangent problem of differential calculus. It introduces where we're going to go, and we're going to get into actual content as far as doing the actual work in a little bit, but just want to give you a roadmap of what's happening. So the outcomes for this section would be describe the tangent problem and how it led to the idea of a derivative, explain how the idea of a limit is involved in solving the tangent problem, recognize a tangent is a curve at a point as the limit of a secant lines, identify instantaneous velocity as the limit of average velocity over a small time interval. Okay, so let's start by talking about lines. So rate of change is one of the most critical concepts in calculus. By the way, this is from the textbook here. We begin our investigation of rates of change by looking at the graphs of three different lines: f of x equals negative 2x minus 3, g of x equals x over 2 plus 1, and h of x equals 2. So if we look at this first one, if we notice, like, given any point, like if we start at this point here, we're going to go one to the right. What happens? So it goes from here down 2. So it goes to the right 1 and then down 2, to the right 1 and down 2, and that corresponds to our negative slope. The next one, if we have a point, let's say here, if you go to the right 1, it goes up a half, or if we go to the right 2, it goes up by 1, or you could say you go up 1 over 2, up 1 over 2, in the positive direction for each. And that corresponds to that x over 2, or that 1/2 slope. And this third one, h of x equals 0, so you all recognize what this is. This is just a horizontal line. And so it has no rise or run. I mean, it has no rise, it has a run. And so this one has a slope of 0. And that slope of 0 is indicative of the rate of change being 0. So as x goes to the right, there is no going up or going down. Now let's look at this other graph here, this k of x equals x squared. So it starts over here on the left, it's going down, 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 down. It bottoms out at the origin, then it starts going up. So in the previous cases, we saw a constant rate of change to where it's going to the right one, down, to the right, then down, then right down, or going to the right, then up, the right, then up, or just staying horizontal, never going up or down. Those are constant. In this one, that rate of change changes. I mean, if we look at f of negative 2, that's going to be negative 2 quantity squared, which is 4. F of negative 1 would be negative 1 squared, which is 1. F of 0 is 0 squared, which is 0. And there's our 4, here's our 1, here's our 0. If we look at f of 1, that's going to be 1 squared, which is 1. F of 2 is 2 squared, which is 4. And so we see when we're on the left side, it's going downhill, or it's a decreasing function, it's an increasing function on the right side. And we could start by trying to find some things like, oh, when we get the slope, we can estimate by looking at the slope between 2 points and try to estimate what's happening with the behavior. In calculus, we could find what the slope is at any given one of these points. Now, if we look at one of the questions you see here in the homework, which of the following has a constant rate of change over the entire domain? So this one is a horizontal line, so that one has constant rate of change. This one is going down, getting steeper, 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 and coming from above. So this is not having a constant rate of change. This one, it's starting to take off. You saw this in your pre-calculus days as an exponential function, but it takes off there. So this is not a constant rate of change. It starts going more and more there. Same thing here. And this one, you remember your trig days, it's like a sine or cosine curve, not a constant rate of change. But this one is a constant rate of change because it's a line. and it's got a slope. Let's see, what would that slope be? Goes through there, and let's see if it goes to another point that we can easily identify. -1, -3, and 4, 0. So that looks like a slope of 7. Okay. Excuse me. So as I said earlier, we could try to estimate what that rate of change might be by looking at 2 points that are on that curve. Now that's not going to be perfect. That's what we call the secant line. So secant line is a line through 2 points and calculating the slope of the resulting line is what we can do. That's called a secant line, is a line through 2 points on a curve. Now, the way the book is identifying it, we have a f of a and x f of x. So here's an example of this blue curve here, and there's this orange line that goes through 2 points on the curve. And we can get the slope of that secant line by doing the f of x minus f of a over x minus a. That's y2 minus y1 over x2 minus x1. And that's our definition of the slope of a secant line. M, we used M for slope. M of the secant line, SEC, and that subscript there means secant line, is f of x minus f of a over x minus a. So the accuracy of approximating the rate of change as the function of a with the secant line depends on how close x is to a. So the further apart they are, like this, it won't get decent, it won't be great, but the closer we could get this second point to our initial point, the more accurate it's going to be. Because if you were to draw a secant line there, it might look something more like this. And here's an example of, that we saw initially. Over there's our x, and then the x is there. It's a little closer. This one looks much more accurate. But if we can get it right on there, we'll have a closer or an exact approximation. So the secant lines themselves approach a line that is called the tangent line. Tangent means it touches it in one spot. Now, given this curve, obviously a tangent line is going to cross the line, but we're not considering that crossing point as one of the points in calculating the slope. The tangent line would be right there. Would just touch right there in that one spot and it'd go through there. So the slope of the tangent line to the graph at A measures the rate of change of the function at A. So that's what the tangent line does. It gives us the rate of change of the function at that point, which is the slope at that point. This value also represents what we call the derivative. So these are things. Rate of change is the same as derivative. The derivative is denoted by this f prime of a, is one of the many ways to denote derivative. F prime at a is the derivative at that point. Differential calculus is the field of calculus concerned with the study of derivatives and their applications. So that's actually going to be, we're in chapter 2, that's a chapter 3 topic, but we're kind of getting some of the groundwork for that now, so you see where we're going to be going with this. And then if I move on to here, this line here, this looks like a little bit bluer line than that blue-green line. That's your actual tangent line. And so the slope of that line would be the instantaneous rate of change at that point. So solving the tangent problem as x approaches a, the secant line approaches the tangent line. So this starts marching closer and closer until we have just that single point. So example, finding slopes of secant lines. So estimate the slope of the tangent line, rate of change, to f of x equals x squared. So remember we saw that earlier, that f of x equals x squared. It looks something like that. I don't know why my pencil's not working right. By finding slopes of the secant line through 1, 1 and each of the following points in the graph. So we saw f of 1 was 1 squared, which is 1. And then another point, f of 2 is 2 squared, which is 4. So that's why they give us the 1, 1 and the 2, 4. So our slope of the secant line would be 4 minus 1 over 2 minus 1, which is 3 over 1, which is 3. So if we were looking at, for example, through there and there, see if I could change colors. Let's see if that does it. Nope. Okay. So that wouldn't exactly be the tangent line, but it'd be an approximation of the tangent line of being 3. Now think of f of 3 halves. That's where they plug it in. They get 3 halves squared is 3 squared over 4, or 2 squared, so 9 over 4. So we had 9 over 4, and then the 1, 1. So we do 9 fourths minus 1 over 3 halves minus 1. 9 fourths minus 1, that'd be 5 fourths. 3 halves minus 1 is 1 half. So 5 fourths times 2 over 1. Wouldn't they give us, we can reduce, I don't know how to exactly, did that choose the color this time? Okay, and then that, hey, it worked. 1, and that's a 2. So we end up with 5 halves as the slope there. And so 5 halves, by the way, I mean, we're talking about a closer point, and then that would be a little more accurate to what the actual slope would be. As we go on, you'll see what the actual slope would be. Okay, so now estimate the slope of the tangent line, rate of change, to f of x equals x squared at x equals 1, as we saw before. So that was at 1, 1, and then the point 5 fourths, 25 sixteenths. So let's get even closer. So if you recall what we had, we would have this curve. Oh, didn't want to draw it all the way. So let me draw it over here. Like so. We have 1, 1. We had the 2, 4. We did the 3 halves 1. So it's right about there. Now we're going to go a little closer. So that means would be the slope of the secant line. It's going to be, I didn't plan to go to black ink, but that's what it is. It's going to be 25 sixteenths minus 1 over 5 fourths minus 1. So 25 sixteenths minus 1 is 16 sixteenths, so I get 9 sixteenths over 5 fourths minus 1 is 1 fourth. So we have 9 sixteenths times 4 over 1, and that reduces down to become 9 fourths, which is 2.25. So we continue our investigation by exploring a related question, keeping in mind that velocity may be thought of as the rate of change of position. Suppose that we have a function s of t. So you typically use s for position functions. That gives the position of an object along the coordinate axis at any given time t. Can we use the same ideas to create a reasonable definition of the instantaneous velocity at time t equals a? Yes, we can. We start by approximating the instantaneous velocity of an average velocity with an average velocity. First, recall that the speed of an object traveling at a constant rate is a ratio of the distance traveled to the length of time it's traveled. Distance equals rate times time. You've seen that before. So our rate is distance over time. So we define average velocity of an object over a period of time to be the change in its position divided by the length of the time period. So this should look familiar. It looks a lot like that slope formula. Let s of t be the position function. The average velocity of a function over time interval at, where a is less than t, is s of t minus s of a over t minus a. As t is chosen closer to a, the average velocity becomes closer to the instantaneous velocity. Note that finding the average velocity of a position function over time interval is essentially the same as finding the slope, as I said, of a secant line. Furthermore, to find the slope of a tangent line at point A, we let the x values approach A and the slope of the secant line. And we look as the trend, what is happening as it gets closer and closer to A. Similarly, to find the instantaneous velocity at time A, we let the t values approach A and the average velocity. This process of letting x or t approach A in the expression is called the limit. And the limit can be a little intimidating at first, trying to do the limit, but over time you'll see that it's not a big deal. And we pretty soon we get past the limits and we're going on to using some different techniques to find derivatives. Okay, so definition. For a position function s of t, the instantaneous velocity at time t equals a is the value that the average velocity approaches on intervals of the form from a to t and t to a. As the values of t become closer and closer to a, provide such a value exists. So here we go. A rock dropped from a height of 64 feet. It is determined that the height in feet above the ground t seconds later is given by this position function. The average velocity of the rock over each, find the average velocity is what we're going to do. So we're looking at it being near t equals 0.5. So we're going to do 0.49 to 0.5 and 0.5 to 0.51. So we're looking at 0.01 seconds on each side of the time we're talking about. And we could then use that to say, okay, if it's this on one side, this on the other, what's it going to be at that point? So let's see, we're going to find s of 0.49. Then we'll find s of 0.5. Then we'll find s of 0.51. And this is just plugging this into a calculator. So we're looking at like negative 16 times 0.49 squared plus 64, negative 16 times 0.5 squared plus 64, and negative 16 times 0.51 squared plus 64. Okay, so I have each of those values calculated out. So we're going to do s of 0.50 minus s of 0.49 divided by 0.50 minus 0.49. And that's going to be that 60.1, no, I got those backwards. That's going to be that 60 minus 60.1584 over 0.01, and that's going to give me negative 15.84. And now let's try the other one. S of 0.51 minus S of 0.5 over 0.51 minus 0.5. That's going to be 59.8384 minus 60 over 0.01, which is what? That gives us negative 16.16. So on the one hand, it's negative 15.84. On the other hand, it's negative 16.16. So I think we can conclude that in between them, the point that it skips over is that we can estimate the instantaneous velocity at time equals 0.5 seconds is negative 16. Does it say meters per second? I think this is feet per second. Yep, feet per second. Okay, hope that makes sense. We had on one side was below it, one side's above it, this is in the middle. Okay, and they have one more example here. The object is moving along the coordinate axis. Okay, now this is t cubed, so we want to know times t equals 2. Estimate the instantaneous velocity by computing its average velocity over time, interval 2 to 2.001. So what we're looking at is s of 2. It's going to be 2 cubed, which is 8. S of 2.001 is 2.001 cubed, which is 8.012006001. So if I'm looking at s of 2.001 minus s of 2 over 2.001 minus 2, that's going to be 8.012006001 minus 8 over 0.001, and that's going to give us 12.006001. So I would estimate the velocity at time equals 2 would be 12 is my guess. 12, and it's say units, doesn't say units per second. Okay, hope that makes sense. Moving on, and that's it for the section.